Hi everybody. I hope you are at home, safe, healthy, and doing fairly well. This is the first lab experiment that we'll be doing remotely, and I wanted to show you the lab setup. So let's take a look. So this is the setup we have for the first part of phase 1, which is the single slit diffraction part. So as you can see, we have a helium neon laser that is shining through a slide, and the slide has a little metal foil, and the metal foil has a number of single slits of varying widths in it. So we are looking at the narrowest of these, and if we take an even closer look, you can see that we're shining it through the 0.02 millimeter slit. So this is making a classic diffraction pattern on our screen, and the screen is a piece of paper taped to a masonite board, and if we get a little closer you can see the diffraction pattern. Of course this is going to be easier to see with the lights out, so let's do that. Okay, so with the lights out you can get a better view of that diffraction pattern. And you can see that wide, central, bright maximum that has on either side a dark spot. So there's a dark spot here, and then there are other bright and dark spots extending out from that central region. So the goal of this part of the lab is going to be to measure where those dark spots are in relation to the very center of the middle bright spot, the very center of the pattern. So I'm going to do that. I'm going to mark with a pencil the locations of all of those dark spots on either side of the central bright spot and extending outward, and then we'll be looking at their locations as a function of order, which is that value of m. So just to the right of the central bright spot we have the m equals 1, and then the m equals 2, 3, and so on. And then to the left we have m equals -1, -2, and so on. So we'll be marking those locations and then analyzing them to see if we can get a measurement for the wavelength of our laser beam. So on this slide you can see the analysis that we'll be doing with the single slit diffraction pattern. The location of the dark spots follows this expression where y, which is the distance from the middle of the pattern out to each dark spot, is equal to m, which is the order number, tells us which dark spot we're looking at, times the wavelength of the light, times d, which is the distance between the slit and the screen, and then divided by w, the width of the slit. So as we can see, if we make a plot of y versus m, then the slope will be equal to lambda d over w. And here we have the setup for phase 1, part 2 of our experiment. Now we are shining the laser through a pair of slits instead of just a single one. So as you can see, the setup is pretty similar. We have our laser and the slide that has the slits. And if we come down and look at the slide, you can see that the spacing between the slits is 0.25 millimeters, and each slit has a width of 0.04 millimeters. So the screen this time is a bit further away. Before it was 0.6 meters, and now it's about 1.5 meters. And so let's turn the lights out and look at this new double slit pattern. Okay, so here we can see the double slit pattern. And as you can see, there's a couple of things going on here. There's two effects that make up this pattern. So first of all, you'll notice there's a lot of little teeny tiny dots. And those little teeny tiny dots are created by the interference between the light coming from the two separate slits. So that's the double slit pattern, and the equation that we have for predicting the double slit bright spots, that gives us those teeny tiny bright spots. But then we have this overall shape caused by the diffraction through each individual slit, and since the overall shape is coming from that individual slit diffraction, it looks a lot like the single slit diffraction pattern. So what you get is this line of teeny tiny dots caused by the double slit, And then some of those teeny tiny dots are getting clobbered by the single slit pattern. So we need to do two things here. We need to write down the locations or mark the locations of those double slit teeny tiny bright spots, count out to the 8th one and find its location. And then we also want to see which of the teeny tiny bright spots is being clobbered by the overall single slit pattern. We want to know where that single slit pattern gives us a dark spot that squelches the teeny tiny bright spot from the double slit pattern.
So as was mentioned previously, the double slit diffraction pattern is made up of two effects. You have interference between the two light coming from the two slits, which gives you these small dots, these tiny dots, and then you have the interference effect from the fact that light is going through a slit, which gives you the effect of the single slit diffraction pattern. And so the single slit dark spot will end up clobbering one of the double slit bright spots. So that means at this location, it's true that the single slit dark spot is in the same location as one of the double slit bright spots. So we're going to find where that takes place, and what the value of m would be 1, and we're going to find which of the bright spots gets clobbered. That gives us our n, and show that this relationship is true. We're also going to find out where the 8th bright spot is in the pattern and show that it obeys this relationship.
And here's the setup for phase 2, option A. Here we're investigating different sized single slits, so single slits of varying widths. So here I have it once again set up on the smallest of the slits. So what we do for this part is measure the distance from the center of the pattern out to the m equals 5 dark spot, so the 5th dark spot on the right, and we do that for the 4 different slit widths that we have available.
By varying the slit width, we're verifying the relationship between y and w, so that if we make a plot of y, the distance from the center of the pattern out to the m equals 5 dark spot, and 1 over w, we should see that the slope is equal to m times lambda times d.
And here we have one of the setups for phase 2 part B, or option B. So this has two setups. The first uses a diffraction grating. So here we have the laser shining through a diffraction grating, and this diffraction grating has 750 lines per millimeter, and you can see the interference pattern that it makes. So with the diffraction grating, you get very widely spaced single bright dots, and we want to measure their positions. Now it's really important when we're doing this part of the lab that first of all, we place the diffraction grating really close to the screen, about 20 centimeters away, because otherwise the dots would go off the edge of the screen. And then we also, when we're doing the analysis for this section, definitely want to not use the small angle approximation, because the angles in this case are not small, unlike the angles for the single and double slit interference patterns. As you can see, one of the diffraction grating superpowers is spreading light of different wavelengths out and making rainbows. So we'll be using this feature in the next lab, because since diffraction gratings can spread light of different colors far apart, it makes it easier to analyze what colors are making up a bit of light. And here we have the setup for the second half of phase 2, option B. So for this one, we have the laser shining between a couple of screens and reflecting off a CD. So it turns out that the grooves on a CD, which is an old-fashioned device that people store music on, those grooves can act like a diffraction grating, and we're reflecting the laser beam off of the CD, and the m equals 0 bright spot is headed directly back towards the laser, but we can catch the m equals -1 and m equals 1 bright spots and measure the distance between those.
The bright spots produced by the diffraction grating and the CD should both follow the same relationship as the bright spots for the double slit. In this case, D would be the separation distance between the closest spaced slits in the diffraction grating or grooves on the CD.
So that's what we have for interference and diffraction. As always, if you have questions, please send me an email. I'll be happy to answer anything that you're wondering about. See you later. Bye-bye.